start the live stream. All right. Alright guys, so welcome back to Excel Island live stream. My name is Abatan Sheriffdeen and welcome to the channel if you're a new subscriber, and welcome back if you're an existing subscriber. So on this channel, I've been learning to upskill myself as a data analyst using the resources on the Datacamp platform for the goal of 100 days. So today is day 76. And so far so good. It has been an interesting journey, trying to learn a technical skills for that couple of days. So I faced a couple of challenges. Like a couple of days ago, that was live stream day 76. So today is day 77. So my gadget developed fault for the fourth time or fifth time again since I've started this live stream. But good news, I've been trying to upgrade my laptop to a gadget that will be more a high performance gadgets that will serve the purpose of something like this, high performance activities like this. But since I couldn't get that easily in the part of the world that I am, so I just have to repair this and continue the live stream. But hopefully within the next few weeks I'll get it sorted out, and I pray and I hope this laptop won't have an issue again, so we can continue the learning journey together. So welcome back to the channel. As I said earlier, so that is a couple of reasons why I haven't live stream for the past 3 days. The last days I've live stream. I do try to take a couple of days to rest, learning technical stuff like that, so that you have a burnout. You have to take a couple of breaks so you can revitalize yourself and come back to learning. Get it now? So back to my learning. So we don't have a choice. We just have to continue like that. Challenges are part of our day-to-day activities, as human beings, or as a technical person. So I'm currently on the career track data analyst in SQL. So if I go to the career track section of Datacamp platform, you see a couple of career track there that you can transition into as a tech person, or you want to transition into new roles as a freelancer, as a technical person. So I'm currently on the data analyst in SQL career track, and I am 83% towards the end of the track. And today is day 76 of my learning journey. I'm trying to make sure that we are live and running. So the goal is, after this data analyst in SQL career track, the next goal is the data analyst in Power BI career track, which I'll also be live streaming that learning journey also. And hopefully I've gotten a new laptop, a better performance laptop that will serve this purpose, so we have a smooth or consistent journey of learning. I'll also be starting this data analysis in Power BI also, so you want to make sure you subscribe right now and put on the notification bell so you'll be the first to know when I go live like this or start the Power BI part of becoming a data analyst. There are also other options there. There's our programmer, SQL server developer, a whole lot there. You can go on Datacamp and check it out. I'll just go back to the progress dashboard and let's learn something new today. But before that, as I said earlier, I didn't say that earlier, but you should also know that I'm a top rated plus freelance data analyst on the Upwork platform. So I've had major success on the platform, and that is due to the influence of a coach, someone who has actually taught me bit by bit, step by step. So his name is Benga Debi, and he currently has a course on right now, which is the freelance client magnet course. And what this course does is that it teaches you how to become a successful freelancer and run a successful freelancing business like this. I'll leave a link to the course under the YouTube description to make sure to check it out. So let's continue learning. So I'll just continue from where I stopped a couple of days ago, understanding data visualization. So this is more like a more theoretical part of the SQL character. So there's less coding here, just more theory. So this contains 4 chapters. So we finished the first chapter of this understanding data visualization on the last live stream. So you can just check it out there and catch up along. So let's talk about visualizing 2 variables. There are also the color and the shape. There are 99 problems, but the plot ain't one of them. Let's continue from visualizing 2 variables. Hold up, let me change my... Okay, cool.
The last chapter focused on visualizing 1 variable. Now we'll move on to 2 variables, beginning with scatterplots. Scatterplots should be used when you have 2 continuous variables and you want to know about their relationship. For example, if one variable increases, does the other one increase too, or does it decrease? Here's a dataset on home prices in 4 cities in Los Angeles County in 2012. The dataset includes the number of bedrooms, the sale price in millions of dollars, and the area in square feet. Here's the scatter plot with the price on the y-axis and the area on the x-axis. To verbally describe this plot, you'd say it's a scatter plot of price versus area. It's okay, but all the points are clustered in the bottom left, making it hard to read. Let's use a logarithmic scale for each axis. On the logarithmic plot, notice that moving right 1 grid line doubles the area, or moving up 1 grid line multiplies the price by a factor of 10. Now the points are more evenly spread throughout the plot. One important concept when interpreting scatter plots is the idea of correlation. Roughly speaking, correlation is a measure of how well you can draw a straight line through the points. If that straight line goes upwards as you move to the right, it's called a positive correlation. If the line goes down as you go to the right, it's called negative correlation. Here are 5 theoretical data sets. The red line in each panel shows what perfect negative correlation would look like. The green lines show perfect positive correlation. In the leftmost panel, you can see an example, strong negative correlation. That means that as the x values increase, the y values decrease. In the rightmost panel, you can see strong positive correlation, meaning that as x increases, so does y. The middle panels show intermediate states. In the third panel, showing no correlation.
When we look at the x-axis here, here's the y-axis, here's the x-axis here. For this strong negative correlation, it says as the we're in chapter 2 now, so I don't have the slide opened. I love the slides to be open. I'll quickly download the slide from here. That is coming up real quick. You can see the slide here. I like following along while following the slide also on my second screen. So I have downloaded it. A minute, please. So I wanted to understand the difference between strong negative, strong positive. You can see the y-axis here. So as the y-axis increases, the x-axis decreases. This one here, as the y-axis increases, are we saying the same thing? You can see the x-axis here is increasing. So as the y-axis decreases, this is the y-axis here, this is the x-axis here. you have to be pretty careful looking at it. So I'm trying to have a good understanding of it. So this is the y-axis. This is the x-axis here. You notice the x-axis towards the right here is increasing. Will you say it is increasing? Well, let me listen to that one more time.
As x increases, so does y. You can see strong positive. That means that as the x values increase, here are 5 theoretical data sets. The red line in each panel shows what perfect negative correlation would look like. The green lines show perfect positive correlation. In the leftmost panel, you can see an example, strong negative correlation.
Okay.
That means that as the x values increase,
it says as the x value increase. So this is the x-axis. As the x increase, it is claiming y decreases. We see the y at that's true though. You can see that at least only few variables are up here. So the variables are coming down. So there are more variables in this section of the y-axis. So but the x-axis is increasing towards the right. Here, if you look at this one, it is the opposite. So there are more variables in this part of the x-axis, but less variables here. That's pretty tricky to understand. Hold up. Let me say it one more time.
Show perfect positive correlation. In the leftmost panel, you can see an example, strong negative correlation. That means that as the x values increase, the y values decrease. In the rightmost panel, you can see strong positive correlation, meaning that as x increases, so does y. The middle.
Exactly. X increases, y increases. X increases, y decreases.
Panels show intermediate states. In the third panel, showing no correlation, the values of y are completely unrelated to the values of x. Here's the data source dozen again. Recall that each dataset had the same correlation, despite looking very different. Correlation makes the most sense if there's a straight line relationship between the x and y values. If you have a more complicated shape, you'll need to be more creative in how you describe the relationship. For example, x and y have a slight negative correlation is not as good a description as the plot looks like a dinosaur. Adding a straight line to a scatter plot is a great way to see if you really do have a linear relationship between the x and y variables. Here, with the logarithmic scales, the trend line has a close fit to the points, suggesting that as the logarithm of the area increases, you get a linear increase in the logarithm of the price. Sometimes a straight line might be a terrible fit. Here, in the price versus area plot, using a linear scale, the line completely misses the more expensive homes. When a straight line trend is a poor fit, one alternative is to use a curve. Having a curve like this can help you to find a way to describe the relationship. Here, by seeing the trend line curve upwards, you can say, as area increases, the price increases faster than linearly. Let's see some examples.
Okay. These are more like technical terms. Maybe the lingua franca. So let's see this now. So interpreting scatter plots. So scatter plots let you explore the relationship between two continuous variables. Here you can see a scatter plot of average life expectancy on the y-axis. So this is the y-axis. Average life expectancy on the y-axis for versus average length of schooling on the x-axis for countries around the world. So each point in the plot represents one country. A straight trend line from a linear regression model is shown. Now says data source United Nations, average length of schooling. I see some countries a year. Average life expectancy 85 years. Average length of schooling 2, 4, 6. Okay. To see that. Yes. Some schools, some countries have average length of schooling of almost 10 years. If you have anyone 11, 12 years here, and the average life expectancy is 75, between 70 and 75. That's quite interesting. It says categorize these statements above about the scatter plot as true or false. No countries have an average life expectancy less than 55 years. That's false now. You are seeing some country here. The average life expectancy is 55. It's saying less than 55. Some are less than 55. That's quite interesting. Which country is that? It says no countries have an average length of schooling less than 6 years and an average life expectancy of more than 75 years. Average length of schooling less than 6 years. Less than 6 years. They are enough here. We have 2, 4. The average length of schooling is less than 6 years and an average life expectancy of more than 75. More than 75. We have a whole lot. That's the first. So if one country has a longer average length of schooling than another country, that country will also have a greater average life expectancy. If a country has a longer average length of schooling, let's see. So let's take this country for example. We have 70. We have 10 years, 12 years, 12. So there are even a whole lot of countries with a longer average length of schooling than another country. That country will also have a greater average life expectancy. That's true. You can say there are a whole lot of countries here with higher average length of schooling and longer life expectancy. It says every country with an average life expectancy of less than 60 years, so from here, has an average length of schooling less than 7 years. That's correct. You can see less than 60 years from here. So there are some countries that have average length of schooling less than 7 years. The 7 years is between years 6 and 8. Some of them are here. So that's true. As the average length of schooling increases, the average life expectancy typically increases. That's true. As the average length of schooling increases, the average life expectancy also increases. I will say that is true. That's definitely true. So exactly one country average more than 40 years of schooling. More than 14 years. Let's see. Exactly one is 14. So we should go back up and see if we have a little country. Slightly, but it is actually on the 14 line. Let's give it a false. No, it's actually outside the 14. It's outside the 14. I will say 2. Or say it is exactly on, slightly outside. There's a negative correlation between the life expectancy and the length of schooling. Negative. If you say that is negative, that can be negative. As the life expectancy, can say as the y-axis, this is the y-axis here, which is the average life expectancies on the y-axis and average length of schooling on the x-axis. So as the y-axis increases, so does the x-axis increases. Is that a negative correlation? No, that should be a strong positive correlation. So this is false. This is false. So there's a positive correlation between life expectancy and the length of schooling. Yes, this is true. I will say this is true. The funny moment, I failed one. 1, 2, 3. If a country has a longer average length of schooling than another country, that country will also have a greater average length. If a country has a longer average length of schooling, that country will also have a greater average life expectancy. Longer average length of schooling, that country will also have a greater average life expectancy. I see schools that have longer average length of schooling here. I see many schools there. They are also way above. But this, I'm certain this is true, but they say it is false. If one country has a longer average length of schooling than another country, that country. So I only missed one, but I'm still not yet convinced about this statement here. Yes, looking at the plots, you could see those countries with higher average length of schooling. Looking at it. That's true. Well, let's see. So that's quite interesting. And that says trends with scatter plots. So adding trend line to a scatter plot can make it easier to articulate the relationship between two variables. That's true. So here you can see the life expectancy for each region again, this time plotted against the gross national income per capita, a measure of how rich the country is. You can have a choice between linear and logarithmic scales on the x-axis and can add linear or curved trend lines. So which statement best describes the trend? So the trend here, so I can either add a linear trend line like this, then to show up. The best is to be a curved trend line. The best will be curved. Can I also do that here? Choose the scale of the x-axis. So you can either change the scale to a linear scale. Okay. If I now use a linear trend line, which doesn't make sense also. But if I change it to a logarithmic scale, if I use a linear trend line, it makes sense. The life expectancy increases linearly with GNI, where GNI is between 1K and 50K. Life expectancy increases linearly with the logarithmic of GNI. Logarithmic of GNI, where GNI is between 1K and 50K. It's almost correct now. This one is almost correct. I'm using logarithmic here. I didn't use linear. I didn't use linear there. So life expectancy decreases when GNI is above 50K. I think the second option is the correct answer. Yeah, I got it. Because I was using logarithmic there. I can see the life expectancy. So the life expectancy increases linearly when I use the linear scale with the logarithmic work. I use the logarithmic. I choose the scale for the x-axis. I use a logarithmic scale, yeah, and I add a linear trend line. I see that life expectancy increases linearly here, from 1K to what? To 50K. And it just started increasing like that. That's true. That's interesting. Line plots. Okay. So we are still in chapter 2. Yeah, we're still in chapter 2. Let's talk about line plots. Line plots are like line charts.
A close relative to the scatter plot is the line plot. Here's a mildly terrifying scatter plot of the cumulative number of cases of COVID-19 coronavirus throughout the world in early 2020. It's okay, but we can make a better plot. Since the x-axis consists of dates, consecutive data points are connected. That means that the plot is easier to understand if we connect those data points. That is, using a line is preferable to points here. So the use case for line plots is the same as for scatter plots, with one extra condition. Consecutive data points are connected in some way. The most common case is that the x-axis represents dates or times, just like you saw with the coronavirus cases, but that isn't always the case. One really useful thing about line plots is that you can draw multiple lines on the same plot and compare them. Here you can see that in February, the majority of cases of COVID-19 were reported in China. Then in March, the rest of the world overtook it. One useful thing to do is to compare line plots to a trend line. Cases of COVID-19 is that you can draw multiple lines on the same plot and compare them. Here you can see that in February, the majority of cases of COVID-19 were reported in China. Then in March, the rest of the world overtook it. One useful thing to do is to compare line plots to a trend line generated from a linear regression. This plot shows the cases reported in China in March, after quarantines and other restrictions were in place. The data line closely follows the straight trend line, indicating that the number of cases is growing linearly. By contrast, if we look at the cases outside of China, a linear trend is a really poor fit. The number of cases is growing much faster than that. By transforming the plot to use a logarithmic scale on the y-axis before fitting the trend line, you see a much better fit. That means that on a worldwide level, the number of cases is growing exponentially. Just because you have a data set where you want to look at the relationship between a numeric variable and time, it doesn't mean a line plot is the best choice. Here you can see the results of a poll by the BBC, where critics were asked to score the best hip-hop songs. In the plot, each point represents a song. Date is on the x-axis, and the critic's score is on the y-axis. Because each song is not connected to the next song, you can't draw a line between them, and a scatter plot makes more sense. To reiterate, line plots need consecutive data values to be conceptually connected. In case you were wondering, the top-rated hip-hop song of all time was Juicy by the Notorious B.I.G. Conversely, you don't always need dates or times on the x-axis. Here you can see a plot of juvenile offenders in Switzerland. The x-axis is time and the y-axis is the number of offenders, and each line represents an age group. Somehow, I find this plot to be very unsatisfying for getting insights. In a later exercise, you'll see an alternative approach without a time x-axis that works better. Time to draw some line plots.
So interpreting line plots. So it says line plots are excellent for comparing two continuous variables where consecutive observations are connected somehow. A common type of line plot is to have dates or times on the x-axis and a numeric quantity on the y-axis. In this case, consecutive observation means values on successive dates like today or tomorrow. By drawing multiple lines on the same plot, you can compare values. The following line plot shows the percentage of households in the United States that adopted each of four technologies: automobiles, refrigerators, stoves, and vehicles from 1930 to 1970. The data source, Panarici and Maclusa, 2019. Categorize these statements about the line plot as true or false. It says in 1945, 2 out of the 4 technologies had lower adoption than 1940. In 1945, this is 1940, 1945 is the middle year, then 1950. So it says 2 out of 4 technologies had lower adoption than 1940. That's true. You can see 1945, 2 technologies, 2 lines are below here. You can see in 1940, almost all the lines are above. You can see, so that's 2. So it took longer for refrigerators to go from 50% adoption to 75% adoption than it took vacuums. So where is the refrigerator? So this is the refrigerator. So refrigerator is green. So refrigerator is green here, and vacuums are purple. Yeah, vacuums are purple here. They say it took longer for refrigerator, let's see, to reach 50% adoption. This 50% adoption. Yeah. It was from 50% to 75% than it took vacuums. It took vacuums. That's false. But look at vacuums here. Vacuums. That's false. It actually took vacuums longer than refrigerator. So in 1940, adoption of stoves was greater than adoption of automobiles. In 1940, stoves. So this is stoves. Adoption of stoves was greater than adoption of automobile. This is automobile here. That's false. So after 1940, adoption of automobiles was always higher than adoption of vacuums. 1940, automobile is red, vacuum is purple. After 1940, adoption of automobiles was always higher. Are they always higher? In 1940, automobile is red. They are literally fighting each other. Let's say that is false. So in 1930, adoption of automobiles was greater than 50%. 1930, automobile was greater than 50%. That's true. In 1940, adoption of refrigerators was always higher than adoption of stoves. Refrigerator, 1940. Refrigerator is this here. Stoves, no. Refrigerator is green. Refrigerator is the green part. And stoves is this. So that is true. And let's see. Yep, we got it. That's quite tricky to grab, but it was interesting. So let's use logarithmic scales for line plots. It says if you have a data set where the values span several orders of magnitude, it can be easier to view them on a logarithmic scale. A subset of the COVID-19 coronavirus data is shown in the line plot. You saw in the video that most of the cases in early 2020 occurred in mainland China. You may wonder what is happening in the rest of the world. Here, the 6 countries with the most number of confirmed cases outside of mainland of China are shown. On the linear scale, notice that moving up one grid line in the plot at this 20,000, 20,000. On the logarithmic scale, moving up one grid line in the plot multiplied by 4. Considering the 6 countries on the plot, which statement is true? It says on the linear scale, moving up one grid line, plot adds what? 30,000. On the logarithmic, let's see. On the logarithmic scale, moving up one grid line in the plot, multiply by 4. Okay. So, considering the 6 countries on the plot, which statement is true? So, which statement is true? So, on February 3, the mainland China, US, had the most cumulative confirmed cases of COVID-19. In mainland, on February 3, I'm currently using the logarithmic scale. On February 3, excluding mainland China, China is not part of the country listed here. Excluding mainland China, excluding mainland China, US had the most cumulative confirmed cases. US is this orange here on February 3. Cumulative cases in the US is 4. Cumulative cases in Germany, that's false. But Germany has, but let's use linear first. If I'm using linear, that's this. If I'm using linear, let's see. If I'm using linear, that is almost true. Germany cases is 5. Spain is 1 on February 3. US is 1. That is even false for either linear and logarithmic. That is on February 7. Germany had more cumulative confirmed cases of COVID-19 than France. On February 17, Germany has 11. Let me play around. Spain. I'm looking for France. So German had 11. Spain. My line is only picking up Spain and Germany. I can't actually pick up France there. For this France there, this red there. Okay, now to pick up France. Oh, this France. My mouse is not picking up France. Let me change it to logarithmic then. So this is France. I can pick up France right now. France at 7. Let's see German. That's true. That's true though, but so I'll go for this first. But on March 2, Iran has less than 1,000 cumulative confirmed cases of COVID-19. On March 2, Iran is green. Iran is the one here. March 2. Iran had less than 1,000. It says less than 1,000. And that's false. Iran is having over 1,000 here. For logarithmic, if I change it to linear scale, let's see. Iran is still the one here. On March 2. You can see. No? Hold up. Iran is over 2,000. So this is false also. Let's look at this last one. On March 16, US had less than 4,000 cumulative confirmed cases of COVID-19. On March 16, the US is the one here. The US had less than 4,000. Yeah, that's true though. You see, March 16, okay, I'm on March 15. It's supposed to be on March 16. US less than 4,000. No, this is more than 4,000. You can see March 16, 4625. So the second option is the correct answer. Wow, got that already earlier. I just have to be sure not to read the plot. Oh, we have one more question here to deal with. Oh, that's interesting. So it says line plots without date on the x-axis. So although date and times are the most common type of variable on the x-axis in line plots, other type of variables are possible. So in the video, you saw data on the ages of juvenile offenders in Switzerland. That data was represented with time on the x-axis and one line for each age. Since that plot wasn't very satisfactory, we'll try again. But this time, age is on the x-axis and there is one line for each year. In the plot, you can see two separate clusters of lines representing different age profiles for the offenders. Which year did the change in age profile of juvenile offenders take place? So which year did the change in age of profile, which year did the change in age profile of juvenile offenders take place? Change in the age profile, the year before. So this one is showing before 2007, since 2007. Change the year to split line by colors. Okay. You can see in 2007, this is before 2007. 2007 is an option. You should start from 2019. Okay, you can see that's which year did the change in the age profile before 2009, since 2009. Let's see 2010. Oh, there's even 2018 here. 2008 here. This time age is on the x-axis and there's one line for each year. Oh, there's one line for each year. Okay, cool. Age is on the x-axis. This is the age here. And there is one line. So each line here represents each year. Cool. Okay. I understand better. In the plot, you can see two separate clusters of lines representing different age profiles for the offenders. Okay. Which year did age? Okay. You can see before 2018. 2008. Okay. Let me go back to 2007. The age profile didn't change before 2007. But since 2007, I bring it 1 year further. It didn't change also because it's still the same thing from here. You can see the age profile is the same thing. Okay. Let's go to 2009. You can see 2009. Oh, hold up. Let's see. That's 2010. The age profile started changing here. Are we looking for the highest age profile? Let's go back to 2009. This change from 14. This is still 14. 14, yeah. We say 14. Which year did the change in age profile? So the change in the age profile take place which year? Let's see. This one is 14. I see having 15. I see having same age here. 15. Age of 15. Oh, hold up. The the age profile is almost the same thing here. But look at 12 here. Let me take a hint. I need a hint. So slide back to see which year. It says slide the slide back and see which year results in one cluster of the line in one color and the other cluster of the line is another color. Exactly. So I think it's 2008, but you can see this one is saying before 2008, since 2008. If I check it again, there's no 2008 in the option here. But let's 2009 to see slide the slider and see which year result is one cluster of lines in one color and the other cluster of line in another color. So the first year should be 2008. You can see one color here. If I go to 2009, so same one cluster, same color. Same color. Until each cluster of line has a single color. Okay. I need to make sure each cluster of line has a single color. Each cluster of line has a single color. That should be 2019. 2018. So slide the slider until each cluster of line has a single color. Each cluster of line. Okay, now I tell you what now has a single color now. Okay. Every line, each year now has a single color. So to see which year did the change in age profile of juvenile offenders take place. If we are going higher, there's no 2012 here. If you are saying 2011, each cluster of line. Let me read. So a mature solution is visualizing juvenile offenders. Line plot doesn't need time on the x-axis. Number work just well. That's not good explanation enough. But let me see if I can grab it and understand it better. So it's saying from year 13 in 2011, there's a change in age profile. But before 2011, okay, let me look at the legend. Probably the legend will make me understand it better. This is before 2011. Before 2011, right? So since 2011, and I'm still trying to compare this better. But sometimes it's like that. You can easily grab it at the first instance or the first explanation. Do you have bar plots here? Let's take a break from today. I think we've learned a lot now. We are like 50 minutes into the live stream. Alright, so that's all for today. I'll see you. We continue on the next live stream, which will be day 78. Alright, so thanks for staying to the end of the live stream. So if you found value in these live streams while learning with me also and upskilling yourself as a data analyst, do support the channel by subscribing and give this video a thumbs up. Let me know your thoughts in the comment section and I'll see you on the 78 live stream. Also, do not forget to check out the freelance client magnet course by my coach Bengadebi using the link in the YouTube description. And I'll see you on the next video on the channel. Do have a wonderful day. Bye.